So hi everybody, I am Dr. Sachidanand Sen and welcome to the third lecture on the battery management system. And today we are going to see about energy storage in electric vehicles. So introduction to energy storage in electric vehicles. So let us now go through briefly why there is a need for energy storage in electric vehicles. What are the key functionalities that we are expecting from the energy storage units? Then what are the basic requirements? Okay. So need for energy storage in electric vehicle. So energy storage means what? It is the heart of the electric vehicle. It determines the range, performance and lifespan. So how long the vehicle will be able to move, that depends upon the battery capacity. Okay, what is the stored energy? Then performance, okay, performance like charging and discharging current. Based upon that, how speed the motor will be able to move. So what is the top speed, what is the top acceleration that it can achieve, then how long the battery will run. So total lifespan, 3 years, 5 years, 7 to 8 years, 10 years. So that also depends upon the type of the battery material that we have considered. So these are the energy storage units. Mostly electric vehicles we are using three broad types that we will see in a moment. So this, like battery is there, hydrogen fuel cell is there, and of course supercapacitor also now being integrated in the view of enhancing the charging speed, okay, to make the electric vehicle charge up at a faster rate. So now these things are replacing the internal combustion fuel tanks, okay, like our IC engines were there. So petrol or diesel vehicles, they are going to be gradually replaced by these things. So the energy storage units must provide high energy density for long range and power density for acceleration. As already mentioned in one of the previous lectures, that energy density is related to the total stored capacity and it will decide how long the vehicle will be able to move. Then power density is related to like how quickly it able to charge and discharge, basically discharge during the acceleration. So performance will be decided based upon the power density. So these are the two important factors. Like one analogy can be generally given in this field, that overhead water tank is there. So that the total water stored in that tank can be representing the energy density, and the pipe through which the water can be coming into the tap. Okay, so the speed of discharge of that water tank, or you can say emptying that water tank, will depend upon the thickness of the pipe. So the total stored energy can be considered to be as the energy density, and power density is how quickly that stored energy can be released. Okay, so that is with respect to time, speed. So that depends upon the thickness of the pipe. So this analogy is commonly used in this domain. So the key functionalities that we are expecting from the energy storage units are to store electrical energy for propulsion, then support regenerative braking. So propulsion means as we are um, pressing the accelerator pedal, what we are expecting the vehicle to move forward, okay, at the desired speed. Then regenerative braking, when we are applying the brakes of the electric vehicle, what we are expecting during that slowing down of the wheels, the kinetic energy need to be converted back into the mechanical energy and then electrical energy through the converters, and that energy should be stored in the battery, so in the process of charging. So whenever we are accelerating, the energy storage or the battery is expected to discharge, and when we are applying the brakes, so some fraction of energy we are expecting it to be again come back to the battery in the process of charging. So these are the two expectations. Then it should also support the auxiliary systems within the vehicle, like lighting, then HVAC system, that is heating, ventilation and air conditioning, then infotainment, so some music players are there. Okay, so those systems, those also require certain power. So expected that the energy storage that we are using, the batteries, they should also be able to support those things. Then interface with the vehicle control unit. See, basically our topic of concentration is that battery management system, and it is a lower level controller. Okay, it is mainly confined to the proper operation of the battery itself. But remember, as a vehicle, as a larger unit, there has to be a higher level controller which will determine how the whole vehicle is operating. So that controller is called vehicle control unit. Okay, so vehicle control unit or electronic control unit. So these are the words that are used for a higher level controller for the vehicles. And battery management system is somewhat lower level, and it is mainly focusing on the proper operation of the battery. So they need to coordinate among themselves. Without proper signals available from the BMS, the decision making of the vehicle control system might not be appropriate. Okay, so these two factors, these two controllers need to operate in tandem with each other. Okay, the typical energy requirement that we are observing is like e-scooter, small vehicles, so 2 to 5 kilowatts. So mostly it is now towards the upper limit only. So around 5 kilowatt hour of capacity we are expecting. The voltage of that vehicle, you can say, it depends upon the capacity of the motor. It does not depend upon the battery capacity. So what should be the terminal voltage? It is determined by the voltage, motor's voltage. Motor means that propulsion unit. Okay, then range of that e-scooter we are expecting to be around 100 to 120. Okay, then passenger cars, four-wheeler, so mainly it is around 50 to 60 kilowatt hours. So at some higher end we will be definitely going for 80 to 100 also. So the voltage range is typically 350 because of the larger size motor, of course. Then the range we are expecting is 250 kilometers to 500 kilometers. So between two major cities, it should be able to travel, it should be able to go to and fro movement, it should be able to go and come back. So then coming to the large buses, so electric buses. So here we are expecting that minimum should be 150 kilowatt hours and maximum it can go up to 400 kilowatt hours. So definitely the size of the motor will again be higher, so it can be ranging between 600 to 800 volts, and definitely the range for a bus is also similar to the range of a car. Of course, bus we are expecting shorter distances. Car, it can be private, so they can move slightly longer. So range can be up to 300 kilometers, and definitely between two bus stops or two major cities, definitely some charging platform need to be provided so that buses can be able to move smoothly. So these are the basic idea regarding the energy storage within a electric vehicles. Now this is the schematic diagram of the representation. So what we are expecting, so you can see here this is a frame or chassis of the vehicle, and here we are having the energy management system, energy storage system, then here we are having the motor. Okay, depending upon the connectivity powertrain we are having. Now types of energy systems that we are expecting. Okay, energy storage. So already mentioned battery, hydrogen fuel cells, supercapacitors are the ones. So any other things like flywheel also can be connected. So a hybrid storage, so or a combination of these two or three, anything can be formed. So that can be considered as the energy storage system. Now what is the task of energy management system? So here we are expecting by the battery management to generate the non-measurable parameters. Okay, so based upon those non-measurable parameters, so what are those parameters? State of charge, okay, state of health. So these things also need to be obtained. Then power and thermal management. So how it is able to share the power, how it is able to note down the temperature, monitor the temperature, control the temperature, regulate the temperature. Then communication networking, as already mentioned, between the vehicle control unit and BMS, there has to be a continuous data sharing. Then fault diagnostic, whether the batteries are able to be isolated if something is going wrong. charge and discharge control, the rate of charging and discharging, is it controllable or not? Then cell monitoring, that continuous voltage and current monitoring of the cells. So these things are the task of a energy management system, or in fact you can say whole battery management system. So these are the issues and challenges. So now, so EV can use one or more combination. Just now I mentioned the different types of energy storage units are there, like battery, then fuel cells, supercapacitors, hybrid storage. Out of this, any of the combination can be formed. So let us now briefly cover the details about the different types of batteries. So electrochemical storage. So battery comes under the electrochemical storage because electricity is involved, and definitely some chemical reactions are taking place at the electrodes, like anode and cathode. So that's why these are uh, classified under the category of electrochemical storages. So most common storage medium is the battery because it is easier to carry, safer as compared to the others, cost effective. Okay. Then it converts chemical energy to electrical energy via redox reactions. Okay. So common types of batteries. Okay. So lithium ion is the most dominant in the modern electric vehicles. Other substitutes and alternatives are also being explored, and they are being developed as required, like nickel metal hydride, okay, used in hybrid electric vehicles. Okay. Then solid state batteries, this I discussed in one of the previous sessions also, like it is emerging, it does not use liquid electrolyte, so there is the chances of leakage will be less, any fire hazards will be less, it is safer, its durability is more, it will run for a longer time duration. So emerging use of solid electrolytes. Okay. Then sodium sulfur, some cheaper options are also being explored as already mentioned. So sodium ion, lithium sulfur, so these are all called futuristic, sustainable, okay, because the materials are abundantly available, like sodium ion. Okay, the low cost alternatives are also being considered. So what are the advantages? So all these batteries means total electrochemical storage. So most of them are having higher energy density as compared to the hydrogen, as compared to the supercapacitor. It is having higher storage capacity within a small unit volume of a battery. Then efficiency is also better. Most of the battery efficiency will be around 80, 85, 90%. So like that. Then compactness. So already mentioned, size is smaller. Then what are the limitations? High temperature. Because of the continuous charging and discharging, definitely the temperature will be increasing, because these are all exothermic. Okay, exothermic and endothermic reactions are there. So in battery we are having the reaction which will release the heat. Okay, so that is because of which the temperature is increasing. So thermal management, raw material dependence, okay, these are some of the limitations that we are facing for the electrochemical storage. Now another type of storage is electrical storage. In electrical storage, what we are expecting is that supercapacitor or ultra capacitor. It is having small energy density, means energy storage capacity is very small, but highest power density, means it can charge or it can discharge very quickly in fraction of seconds. Okay, so stores energy electrostatistically. Okay, we will not go into the fundamentals, like as how a capacitor works, it is also having similar features. So it will store the energy in the form of electrostatic and not chemically. Okay, between two parallel plates these things are aligned like that. So deliver very high power. Okay, but low energy. Just now I mentioned high power density but low energy. So used for regenerative braking. So suddenly you are pressing the brake, so it will quickly extract that kinetic energy, convert it into electrical energy, and it will charge the supercapacitor for regenerative braking and power smoothing. So whenever sudden acceleration is required, the battery discharging current is around its peak. Suppose it is around its maximum capacity. So so it cannot contribute further in the required acceleration, okay, maneuver. So in that case, the supercapacitor will act as a supporting, so it will release or it will give some of the discharging current. So with that, the vehicle will be able to accelerate in a better way. But of course, that contribution will be for a short duration only, because as soon as it starts supporting, the rate at which it will discharge will be very faster. But of course, acceleration we are doing for fraction of seconds only, okay, 2 seconds, 5 seconds, 10 seconds, like that. So it will be definitely quite helpful during the required acceleration for the electric vehicle. So lifespan, so number of charging and discharging cycles. So for battery, it is maximum it can go up to suppose 10,000 cycles, that too for solid state battery. But in case of supercapacitor, it can go up to 1 million also, like 10 lakh cycles. So complete charging and discharging cycles, it can go up to 10 lakhs. So now coming to the electrical another type, that is hybrid energy storage system. So like combination of battery and supercapacitor can be done. Okay, battery supplies the energy, as already mentioned. Batteries are having higher energy density, it can store larger amount of energy, and supercapacitors handles the peak powers. Okay, for a short duration it will be able to support the peak load demand during the high acceleration, and it will also help as the lifespan of the supercapacitor is quite large, so it will definitely help to extend the life of the battery also. Okay, so this is what we are possibly able to combine. First combination that we have learned, that is supercapacitor and the battery. So this gives a better clear picture about the things that we are now discussing, that hybrid energy storage. Here you can see battery is there, okay, supercapacitor is there, and supercapacitor means DC to DC converter will be there, and in battery definitely here also we can have a voltage regulator or a DC to DC converter, but definitely the motor is working in AC. So one inverter is definitely required to convert the DC into AC supply. So this domain here we are getting DC only, and supercapacitor DC to DC converter is definitely required, because the voltage level at which the supercapacitor operates and the voltage level at which the battery operates, that will be quite different. Okay, so definitely we need to have a converter here. Now inverter, it changes the DC supply into AC and feeds into the motor, and motor will run, and through the powertrain or drive train, it will make the wheels rotate and the vehicle will expected to be moved. So this side, so along these converters, inverter, then energy storage units, these are coming under the electrical part of the electric vehicles. Now mechanical part will be the motors. Of course, motors can also be considered as the electrical one, but as the rotating components are involved, more or less it will be taken as a part of mechanical systems. Okay, and regenerative braking, when the vehicles are applying the brakes, okay, so wheels should be able to convert it back, and that high kinetic energy should be converted back into the motor, and it will be fed back through the inverter. So these are bidirectional. Okay, so here again it will be going back to the battery, or you can say supercapacitor. Okay, now come to mechanical energy storages. So as already mentioned, flywheel is also a possible choice, and lastly hydrogen fuel cells. These are the latest trending things that we are considering. So here mechanical means, although it is rarely used, but for experimentation, for some prototype development, some study related to multiple combination of energy storage units. So this can be also taken into account. So mechanical energy storage flywheel. So previously also I have mentioned what is a flywheel. It is a large rotating mass. Okay, it will gain, it is operated within a vacuum. Okay, cylindrical vacuum will be there, and a cylindrical body will be rotating, and as the energy is accepted or charging is taking, so it will speed up, it will accelerate further, or okay, it will accelerate further, and during discharging it will decelerate and it will provide the energy to back to the grid. So receiving the energy and providing back. So that is how the flywheel works. So stores kinetic energy in a rotating mass. Okay. So higher power density and quick response. As it is continuously rotating, it can resemble a generator, typical generator. Okay. So sudden load is there, it can definitely provide it. Okay, because of its inertia. So higher inertia is it is having higher inertia. So quick response we can expect. So used in high performance electric vehicles, buses for regenerative braking. As already mentioned, flywheels are not used in most of the typical four-wheelers or two-wheelers because of the otherwise gyro effect will come. The vehicle is moving and if something is continuously rotating on behalf of energy storage, so that might create some balancing issues. Okay, so it is mainly suitable for higher vehicles or where some typical performance is expected, so that buses it can be used, or that, but that also should be a smaller, comparatively smaller size. Okay, then just to support the additional speed, what are the limitations that we are having in the flywheels? So mechanical losses, high cost, okay, heavy design. So these are the issues because continuous rotation is there. So mechanical wear and tear will be taking place. Okay, cost is high because maintaining that type of energy storage is not feasible also economically, and heavy design is required. Okay, that's why it is not preferred option for the energy storage. Okay, the chemical energy storage. So hydrogen based hydrogen tank will be there and a fuel cell has to be installed within the electric vehicle, which will be able to convert that stored hydrogen by mixing it with the oxygen or air and releases water as well as the energy. So fuel cell electric vehicles use hydrogen as energy carriers. Okay, so this is a simple reaction, chemical reaction that is taking place within the fuel cell. So hydrogen plus oxygen we are combining from the air. Okay, hydrogen is released to the channel, okay, pipes through which it will be going to the fuel cells, and that water will be generated and heat will be of course generated, then electric energy will be obtained. So it is having somewhat higher efficiency. Okay, but of course it is not comparable to the battery. Battery is above 80%, and whereas fuel cell it is around 50 to 60%, that to maximum at present available innovation and technology. So, but as the size of the hydrogen can be enhanced, hydrogen tank can be increased, so it can go up to longer range because battery it's heavy, it will have some limited space only. Okay, so up to 500, 600 battery can move maximum. Similarly, hydrogen also, if we are adding hydrogen tank, larger hydrogen tank, so it can also easily cover up to 600 plus kilometers. So what are the basic examples that we are already having hydrogen based electric vehicles are Toyota Mirai, Hyundai Nexo. So these companies, Toyota and Hyundai, are the leading vehicle manufacturers. They are already having these hydrogen fuel cells. Okay, so hydrogen storage method. So there are different methods. In fact, next session we are going to learn about all these things in detail. That is methods of hydrogen storage. It can be stored in the form of compressed gas, then liquid hydrogen, then metal hydrides. Okay, liquid hydrogen and metal hydrides. Okay, liquid form, gas form, and metal means it is of course coming under solid. So different forms it can be stored. Now lithium ion based batteries. So most widely used batteries are the lithium ion. So let us learn about different types of lithium ion batteries and what are the charging discharging cycles that we are having. Okay, so most widely used due to high energy density and cycle life. Okay, so common chemistries are, chemistry means what are the components these can be prepared of. Okay, lithium will be the common element. So NMC, nickel, manganese and cobalt. Okay, this can be combined, any two, any three, or any one can be formed. So balanced energy power used in Tesla and Hyundai. Okay, then lithium iron phosphate, this also we have discussed in previous video. So lithium iron phosphate, it is safer, longer life cycle and used in Indian electric vehicles like Tata and BYD. BYD is a Chinese company. Then NCA, so nickel, cobalt and aluminium. Okay, lithium is common, remember, in all. Then nickel, cobalt and aluminium. Any of these combination, high energy density used in premium electric vehicles. So higher energy density and of course it will be more costly. So only suitable for premium electric vehicles. So these are the names of the um, types of lithium ion batteries, and last one, a comparison is done with the solid state batteries. So here you can see NMC means the first category, the energy density is watt hour per kg, so it is typically ranging between 220 to 260. Okay, cycle life is around 2000 to 3000. Okay, then safety case, moderate, it is somewhat moderately safety and cost is high. Similarly, second category, that is lithium iron phosphate. Okay, so it is energy density is lower. In fact, it is having the least energy density and its cost is medium, but cycle life is somewhat more, 3000 to 5000 cycles, and safety, it is excellent safety. And highest energy density up to 280 we can achieve in case of the third category, that is nickel, cobalt and aluminium. But the cycle life is quite smaller, safety is moderate and its cost is also higher. Okay, whereas the solid state battery, where the liquid electrolyte is not there, so it is having highest energy density up to 350 to 450. Life cycle life is more than 5000 and it is most safe. Okay, it is excellent, but its cost is very high. Okay, so this is just a basic comparison between different options of the batteries that we are currently having, and a comparison in terms of energy density, cycle life, safety and cost. So this diagram typically shows the complete architecture of interfacing the energy storage devices with the uh, motor. Okay, so energy storage, already this just now we have covered this one. Electrochemical battery, so different types of batteries options, these are mentioned here. Lead acid can be there, although that is not suitable for electric vehicles. Then nickel based is there, air based, zinc based, okay, vanadium redox, lithium based, these things are available for the battery. Then chemical based means hydrogen, fuel cells, synthetic, natural gas can also be used, biofuels can be also considered. Okay, static, okay, electrostatic, or no, this is electromagnetic. So although supercapacitor comes under electrostatic, then another category is superconducting magnetic energy storage. So this can also be explored to be integrated, but of course cost is more. Then hybrid, combination of any of these. Okay, so battery plus supercapacitor, battery plus fuel cell, supercapacitor and fuel cell, or combination of these three. So if these three are combined, you can see fuel cell, battery, supercapacitor, all of these will be definitely having different structures of DC-DC converters. Then a DC bus will be connected, and after that one inverter will be required to have. Then only we will be able to feed the electricity to the motor or the load. Okay, so this is the complete integration architecture of the energy storage devices. So solid state batteries. Okay, so briefly we will cover different batteries till we are learning about that one. So replace liquid electrolyte, all these things already I have mentioned in the previous videos. So liquid electrolyte with solid ceramic or polymer electrolyte. So here no liquid electrolyte is used. Okay, replaces the liquid electrolytes with solid ceramic or polymer electrodes. So advantages already mentioned, these are higher safety. Okay, fast charging we are able to achieve, 50 to 100% higher energy density we are having, but challenges are these are more costly. Okay, then scalability issues, because large scale production is not yet achieved till now. Then material interfaces, okay, different materials also need to be extracted and interfaced. Then nickel metal hydride, okay, nickel metal hydride used in hybrid vehicles such as Toyota Prius. Okay, so this is also one of the replacement of lithium ion, we are also going for nickel metal hydride. So low energy density than lithium, but robust for partial state of charge operation. So up to a certain extent it can match the operation of the lithium ion. Okay. Then emerging technologies that we are having, sodium ion, already mentioned in the previous lecture. So cheaper options and more sustainable based materials that are being considered, like abundant material, because sodium is abundant, low cost, silicon anode batteries, which is 3 times higher capacity potential than graphite based, sulfur, lithium sulfur based, okay, higher power density, higher energy density and lighter weight, okay, dual ion or proton based batteries, these are all in the R&D stage right now, okay. So this is a complete battery technologies. So how the battery management system is operated, that can be clearly visualized here. Energy management system, typically we will do some testing based simulation, okay, test cycles we will be running. Then hydrogen tank and PEM based fuel cell will be there. Okay, proton exchange membrane is there. Then battery and supercapacitor combination is there. So they are connected through monitoring devices which will monitor the state of charge, okay, high state of charge. So DC to DC converter is there. Here it is also having its own DC to DC converter, and at the end DC bus link is maintained, then DC to inverter, then electric motor. So this is also typically showing one of the previous slides in a detailed manner. Okay, so how to maintain the DC bus link voltage constant, okay, DC bus link converter for these two also need to be maintained. DFC duty cycle, okay, then power delivered duty cycle of these two things also. So these all things are managed by the energy management systems. So performance matrices, okay. So what are the things that we need to consider while selecting the type of energy storage? Are typically specific energy. Specific energy means per unit volume, okay. So or kg mass you can mention. So watt hour per kg energy unit is watt hour. Per kg means determines the range, okay. Specific power. So watt per kg determines acceleration capability. Life cycle. So number of charging and discharging cycle it can undergo, okay, before its state of health is reducing up to 80%. Okay, so what is how state of charge is estimated, how state of charge state of health is estimated, that we are going to learn in the subsequent lectures. Okay, so the 80% is the retention. So once the 80% retention capacity is reduced, it will be end of the life of the battery for the electric vehicles, and we will have to go for second life or some other alternate usage, like I have discussed this in the first lecture on sustainability. Okay, so second life usage is also considered. Then C rate, how quickly charging and discharging is allowed. So one C rate means full charging or discharging in 1 hour. Suppose 2 C rate is there, so it will be charging and discharging in half an hour, okay. So full capacity divided by time it is taking, okay, to charge, okay. So if it is 5 means 5 C rate means it will be charged and discharged in 1 hour divided by 5, okay. So in 12 minutes. So like that we are able to decide what should be the charging and discharging cycles. So presently BYD companies, Chinese companies, they have developed a 10C rate of batteries. Okay, means within 6 seconds it can fully charge the batteries. But of course, keep in mind that the thermal efficiency of those batteries will be different. Different materials, high cost, all those things will be coming into picture. Okay, so round trip efficiency. So what is the battery? Typical battery efficiency is between 80 to 95%. So mostly it can be for lithium ion slightly higher. So about 85 to 95%. So these are the basic details that we need to consider while selecting the type of battery. A small example that we can see here. Suppose if some certain number of modules are arranged in series just to increase the voltage, and parallel connection of such series connected cells are the number of parallel connection will be to increase the capacity. So suppose 400 volt electric vehicle pack where 100 cells in series are connected with 4 volt each. So we are having 400 volt electric EV voltage, terminal voltage is 400. Now 50 ampere hour, total each cell is having 50 ampere hour. Then what will be the total capacity? So 50 ampere hour into 400, so it will be around 20 kilowatt hour. So like that we can determine the capacity of the battery. So battery management system monitors temperature, voltage, current, state of charge, state of health, all these things. Similarly, thermal management is also a part of the or responsibility of the battery management system, essential for safety and longevity. Okay, techniques like air cooling, low cost, then limited efficiency, liquid cooling used in high performance EVs. Okay, then phase change materials. Okay, air cooling, liquid cooling, phase changing like paraffin wax. We are using paraffin wax. When the temperature is exceeding, that solid wax will be melting. So it will flow in a better way through the channels. So it will be able to extract the heat properly. Okay, so advanced passive cooling techniques, these are the things. And optimal battery operation will be between normal temperature, between 20 to 40 degree, and it can go up to 60 degree maximum. Okay, beyond that it will definitely, performance will be degraded in a faster rate. Okay, especially during the summer, the chances of catching fire will be more. Okay, now charging and energy recovery. So these are some additional topics that we are learning about. So what are the charging methods like fast charging? Okay, channels where lithium plating and thermal runaway risk is there. Okay, smart charging integrates grid demand. Okay, so if proper charging channels are used, the vehicle can be used for integrating with the grid also. Okay, so it can act as energy buffer. It can absorb during surplus generation and it will be able to deliver. So these things also I have discussed in second video on the energy storage options. Okay, so smart charging integrates grid demand responses like in the vehicle to grid operations. Then regenerative braking, already mentioned, it converts the kinetic energy into electrical energy during braking, improves energy efficiency by up to 25%, 15 to 25%, controlled by inverter and motor in generator mode. Okay, so vehicle to grid operation, power, bidirectional power flow will be there, enables grid support, frequency regulation and renewable balancing. These things already discussed. So these are the three typical broad type of charging infrastructure that is required. Level 1 charging like household. Okay, level where for small bikes we are having, and it will take overnight charging 8 to 10 hours. Okay, level 2 is somewhat faster and commercial charging, and 2 to 22 kilowatt. Okay, some 4 to 6 hours it will take. And DC fast charging, it is typically installed at charging stations. Okay, it is only for commercial purpose. So within 20 minutes to 60 minutes, any battery can be made fully charged. Okay, that is coming in the DC fast charging. Then electric vehicle chargers location. So how to select the proper location? So like level 1 charging, urban planning and proximity to land use. Okay, transport infrastructure and parking facility. Like households you can have. Level 2 generally population density is more, proximity to public services, some public garden is there, shopping mall, hospitals. Okay, proximity to transport hubs, density of marked or controlled parking spaces, share of households without private parking space. So in those places level 2 can be installed. Level 3 is basically schools, universities, hospitals, public administrative buildings. In such places these things can be installed. Then EV charging method based on physical contact. Okay, how the EV can be charged. Okay, so conducting charging, battery swapping, wireless charging. So wireless charging are typically 3 types. Also, although these are not coming under that battery management system. Okay, just overview I am giving. We won't cover all these things in detail. So different types of wireless charging are there: capacitive, inductive, and resonant inductive. Okay, static and dynamic. Then these are the typical through wired connection. Okay, charging 3 levels that we have just now seen. Okay, then stability, safety, and recycling. Okay, so stability challenges, okay, sustainability challenges that we have already discussed, that mining of lithium, okay, nickel, cobalt, hazardous materials are there, environmental and ethical issues will come, then recycling material, how the recycling is done, all these things I have already discussed, fire-based, water-based, direct recycling, okay, pyrometallurgical, hydrometallurgical, then second life usage, this also I have discussed in the video one of on sustainability of the batteries. Okay, retired electric vehicles should be considered for stationary stored usage, microgrids and UPS systems. Okay. Then the final slide. So the key takeaways from the today's lecture is, so EV batteries are critical determinant of range, cost and performance. Okay, so size should be selected properly. EVs use diverse energy storage technologies like batteries, okay, primary batteries. So primary battery is always considered to be the primary source of energy in any hybrid combination of different sources. Okay, then hybrid system optimize power and energy delivery, safety, cost, recycling and energy density are major design drivers. Okay, lithium ion dominates, but solid states and sodium ion are more promising for future. Okay, because it is low cost, it is having higher safety and energy density. Life cycle is more. Okay, so safer and cheaper alternatives will be always in search. Okay, then battery management system, thermal cooling, recycling essential for sustainable operations. Okay, so future of EVs will feature smart storage, bi-directional charging and integrated renewable sources. So the questions that we can ask from today's lecture are hybrid energy systems. Why are becoming more popular? Okay. Then how hydrogen fuel cells combine battery EV in long distance transports. Okay. So what are the sustainability challenges that we are facing in the recycling? Okay. So with this we will stop this lecture, and next class we will again discuss about the hydrogen as the energy storage for electric vehicles. So thank you very much.